Hello, everyone. Thank you for coming to this event. I'm one of the co-organizers of PyData Yerevan, and today Mark will introduce you to the visual document retrieval as a topic. Thank you and enjoy the event.
Thank you. Okay, hi everyone. I'm Mark. I'm a machine learning team lead in Metric company, and I also teach some classes in Yerevan State University and American University in Armenia. And as already said, we'll talk about the visual document retrieval. So firstly, I will talk about what are the applications of and what is visual document retrieval. And in the end, I will talk about the research that we are doing in our company directly connected with this topic. So let's go. Okay, as you have guessed, the retrieval part is coming from the retrieval augmented generation. So very briefly, what it is, whenever we have some external knowledge and we want our LLM to use that external knowledge for giving more accurate answers, more good answers, personalized answers according to our knowledge, we use the retrieval augmented generation. So we don't rely only the knowledge of the LLM, we feed external materials to it. So if we separate in two parts, it has retrieval phase and the generation phase. So for the retrieval phase, we have this part. So given a query, the system retrieves relevant information from external knowledge, whether it's from database, vector store, or document collection, or anything else. And the second step is the generation phase. So we retrieve some documents, we have external knowledge. Now our large language model, whether it's open source or closed source, will use that knowledge and its external knowledge to do different tasks, answer questions, do extraction, or anything else. Okay, the concentration is this retrieval part. So the generation phase, we'll leave it for future research. And let's see what's the steps of the retrieval usually. Okay, so for the retrieval, we have the following stages. First of all, we need to have external knowledge and we need to process it. So if we have a textual information, we need to have textual chunking, store that chunks in VectorDB, do some other things for post-processing of the text. Then we need to have queries, which is given by a user or by us. And with these queries, we can use the raw query, or we can have query augmentation or some other techniques. And the retrieval part, given the query. So we have the query, we have all the chunks and everything stored in DB. We do this search. So there are different search methods, BM25, vector search, or the hybrid search, combining these two together. So given a query, we get the correct chunk. Okay, so far we talked about the textual data. So what if we have documents? What is the difference between the documents retrieval stage and the simple retrieval stage? Let's see. Okay, if you have a lot of PDFs, scanned PDFs, or not scans, these are the steps that are being added to our normal pipeline. So first part is that we need, in order to have text from the PDFs, we need to do extraction. So we need to apply some OCR engines there to get the text from the scanned document. Later, we need to do some layout processing because we have the raw text, but our document is structured. It has headers, paragraphs, the main body. So in order to LLM to perceive that information, we kind of want to do layout processing and transforming text into the markdown format or other formats. Then the other steps are more or less same. Okay, but there are a lot of questions rising here. whenever doing these processes. So first of all, how do we get the good layout structure? What is the best layout structure there? Because there is the markdown formatting. Maybe we need to put the HTML formatting there. Maybe we need to have Latin formatting or some other stuff, maybe XLM tags and stuff. What is the size of the correct chunk? So how do we decide the length of the chunks? Maybe if we take too big chunk, it will like interfere LLM to answer correctly. If you have small chunks, then maybe some information are being missed out. And other question, what if we have charts, graphs, or images in our document? So OCR cannot like correctly understand the image, or it can like take the chart numbers, but the chart, the visual part will be left out there. So to all these questions are arising whenever we're trying to work with documents in a retrieval part. So that's why some guys from France, if I'm not mistaken, they come up with a good solution to this. So instead of using complex retrieval systems that rely on OCR or document layout, information recognition, all that crappy stuff, they decide to, let's just embed the image and have a model that will do everything above mentioned for us. And they came up with the ColPaLi, efficient document retrieval with vision language models. So here is the first place that the visual part in a LLM is being introduced here. Okay. So let's go further and see what is happening behind ColPaLi. Okay, in the upper part, we see the standard retrieval method. So on that part, we have the queries. It goes under the text embedding model, and we have embedding for our text. On this part, we have the page, we do OCR, layout detection, we do captioning, chunking, or other stuff. And finally, we have like embeddings for that part, and then we do similarity like computation. In ColPaLi part, we keep the textual embedding part in place, and we replace this part mainly with vision LLM. And keep in mind that the two LLMs are the same, so we don't have like two different models. It's one single VLM. And we like do simple chunking here, give it to vision encoder, LLM, we get embeddings, and we'll talk about this maxim part and similarity score a little bit later. So basically, this is the idea. And the good thing is that this NDCG is a metric, so it gets quite higher score compared to the standard retrieval, this part. And also, per page processing, the throughput is quite fast. So 0.39 seconds for single page and around 7 seconds on the standard retrieval calculations. Okay, let's see what is behind the ColPaLi. The original model that I used is PyGemma 2. So this is a VLM already trained on some tasks. So the architecture is quite simple. They have image encoder, which is the SIGLIP. They have some linear projection that projects this vision output into the text space. And on the other hand, we have the text input. These linear projected vision tokens and text tokens are being concatenated with each other, and it goes as an input to the Gemma 2 LLM, and we get the text output. This is the VLM structure that are mainly used in almost all VLMs. And actually, they used specifically PyGemma and like they added this call part and come up with the ColPaLi, but it doesn't necessarily have to be this specific model in order for this method to work. So it can be called anything. It can be any VLM, like Quen VLM or Swan VLM or anything. It can be put there, and it with the proper training, it will work. And it doesn't even need to be a VLM after all. It can be just a separate vision model and a separate LLM that are not connected and never have been trained as a full VLM. So let's say we can take a SIGLIP as an encoder and Qwen as an LLM. And of course, having pre-trained VLM would boost a little bit the performance, but it doesn't mean that only that, with that approach it would work. I will show in our research that it worked. And even we tried to have like a vision model and a text embedding model with each other, and it also works with this strategy. Okay. So as you know, like the LLMs and VLMs, they are outputting, generating text. So for the embedding model, we don't need this generation part. So we have our normal decoder transformer. In order to have the embedding part, we need to remove this linear and softmax projection and generation of the text. And all this will give us the embedding, like the latent space of the inputted vectors. So here we have like decoder blocks, like multiple blocks, and in the end we will have same shape as the input and some dimension as a vector, like hidden dimension of the inputted whatever it is. Okay, and where does the call part come from? So there was this paper which is called Colbert and late interaction. So what they're saying that there are like different ways that standard retrieval are being done. As you can see, we have like two different models that is processing query and the other model is processing document, and then later the similarity is being calculated. In those two, like the documents and queries are interconnected with each other before going to the model, and after that all the computations are done. And the last part is the late interaction and Colbert structure, which is different from the other ones. So the main difference is that, especially these two, they are not like they do not provide opportunity for us to pre-compute the embeddings of documents and queries, because this interaction have to happen like before the model prediction. So if we have a lot of documents and queries, we need to do these computations online on that specific moment that we want to do something. With first and last one, we can like pre-compute, like if we have tons of documents, we just pre-compute the embeddings, we store it somewhere, and then during the live phase, the query comes, we just calculate this similarity score with the embeddings only. And it makes like overall the pipeline, the product and everything very fast and efficient. Now let's deep dive into this late interaction part and see what is happening. So usually for each inputted query and document, we in the end get one whole vector of which represents the whole query, and one vector which represents the whole document in standard cases. Here they are saying, okay, this is not going to be very good, because one embedding is not going to represent a lot of text or a lot of document in our case. It's not going to represent it in a good way. So instead of having like this one query in the end, let's keep the amount of tokens that are being input as a query in this document in this page. So these ones are already the embeddings of the inputted query in document. And for each query, they are going and calculating maximum similarity of this specific query and all document embeddings. First one they find the maximum similar one, they get this score. For the second one, they do the same. For the third one, they do the same. And then they sum all together and get one score there. Clear? Yeah. Okay, this is the late interaction part. So same for ColPaLi. They like took this idea from Goldberg and make it further to work with documents directly. As you can see, the same thing happens here. For the document, it divides it into the patches, in this case 4. They get 4 embeddings here. So we have 3 tokens there, we have 3 embeddings there, and for each text token embedding, maximum similarity of these 4 is being calculated, and then for the 3 ones, the sum of these is being the similarity score overall. Okay, and one last thing that they are also doing, which is important here, this is the all code for the ColPaLi. One more thing is that our LLM is giving out the hidden dimension, which can be quite long. So in the ColPaLi case, which is the polygemma model there, so they do the model prediction, the model forward part, and this is the last hidden state. So for the last hidden state, the hidden size is 2048. For some models, it can be 4000 or something higher. And this is like really long embedding for us to store, and taking into account that we are also storing the as much embeddings as the sequence length. It will be like a huge overhead for our vector DB. So they introduced this just small dimension, 128, and only added this last layer after the last hidden state. So this is just a simple NN linear layer with the hidden size and the output dimension. So after this, we had batch size, sequence length, and hidden size, which is 2048. After this line, they are getting batch size, sequence length, and 128 dimension. So they like squeeze dimension more than 20 times there. And let's see what's happening with the loss. So usually the upper part is the late interaction part, the formula for it. So EQ is the embedding of the queries, and embedding of documents is ED, so the max sum is happening there. And as usually, the embedding models are being trained with the contrastive loss. In our case, ColPaLi used in-batch pairwise cross entropy loss. So what they did is, in the batch, each query has a corresponding image as a matching to each other. So they are trying to maximize the similarity score. So SK is the late interaction score, you can see over there. So they are trying to maximize the similarity score of the correct match, and they are trying to minimize in the denominator the score of the hardest negative matching pair. So the difference is that they are not compared to other losses like InfoNSE, they are not calculating the maximizing the difference between matching and not matching all other pairs in the batch, but they are maximizing the matching part and minimizing the hardest, second highest linear interaction score having negative sample there. Okay, we can come back later if you have any questions, but yeah, the formula and everything is there. Okay, so let's move. For data, it's nothing very sophisticated. They have, for this we need to have query and image, page images in order to train this model. So they gathered 180,000 query page pairs. 63% they took from the openly available academic data sets, and for the 37% they have a lot of PDFs scraped from the web. And for each one, they generated like some queries using Claude 3 Sonnet, and like have 37% synthetically generated queries for real PDF documents here. These are some like samples of the data they used. So some samples from government reports. You can see that there are like tables, some visualizations, charts, and also some chemical like formulas and the visualizations. So different things. So it's not only just a page with the text. Besides this model and training and data, they also introduced the VDORA benchmark. Like there is a benchmark, good benchmark for text embedding models, the MTEB one, and there is no good benchmark for the document retrieval models. That's why they like gather some data and introduce this benchmark, so a lot of other researchers can develop their models and put there and compare with each other everything. So they have overall 10 data sets with this number of queries and documents. And whenever you have a model, you go evaluate and compare with other models. And finally, the results. They show that their method is, you don't see the numbers, but not very important. Let's put it here. They are winning on all benchmarks for different VLMs, pre-LLM like searches, BM25, and other stuff. Also, here the interesting part, you can see that there are some models that are called PyPaLi. So this is the standard method instead of call. You remember for the call we have this maxim similarity score with late interaction. In the PyPaLi method, they take like for the input, they like average this, and for queries and documents, and they have just one vector for query and one vector for documents. The standard method. And they also show that with this method, the scores are significantly lower. So the average from all of these data sets is 58. With the PyPaLi, the model is completely same. And for the ColPaLi, it is 81, which is very significant in research. Okay, this is all about the ColPaLi and VDORA. Now let's see what we are doing here. So our goals are that we want to create a state-of-the-art model for visual document retrieval, so best in the world. We want to do it open source, so no proprietary things. Everything we do, we also need to share, so contribution to open source. And the third and important thing, in order for this method to completely replace the standard retrieval methods, we need to have much more efficient models. These are our research goals connected to the visual document retrieval direction. And currently we have several models that are open sourced. These are mainly Qwen models, because during our last research, we understood that the Qwen model is kind of the best model that is there open source, working with documents. That's why whatever we do is mainly with Qwen. This is from our past knowledge. And you can see different versions and different sizes of models. And the last one is a combination of Qwen and Stella embedding models. And can you guess what is the model of like the behind model for Stella? Qwen, right. Okay. And let's see what is the main things that we changed in order to have a good model. From the benchmark, we saw that the main issue for different models is that they are not working good with documents that have like a lot of text. So there are like some visualizations and things there, but for the DocVQA, for example, dataset, which has average score of 60, we saw that this is heavily documents with a lot of text there. That's why one thing to improve overall model and performance, besides taking the ColPaLi dataset as a training, we also added a couple of datasets that are heavily for like documents with a lot of text. So we added around 150K pairs, query and image. And the next thing that usually are done is we do a lot of hyperparameter tuning. We experimented with learning rates, LoRa parameters, and different batch sizes. I mean, we did a lot of other things, but these are the three parameters that heavily impacted the performance for our models. And let's in detail see what is the in behind for our model. So for Qwen multilingual, yeah, I forgot to say that one of the models, one of the datasets we added is also multilingual, so it can work not only with English documents but also in different languages. I'm not saying that like very low languages with low resources, so Armenian is not there, unfortunately, but French, Italian, German, English, obviously, and Spanish are there. Okay, so in order to get the Qwen models, we use the Qwen 2.5 vision language model, which is 3 billion parameters. We trained it with ColPaLi-style training, the multiple query and max similarity. So data is around 250K query image pairs. Overall, we trained for 5 epochs, and we trained only LoRa. So we did LoRa training, and we've kept frozen the vision part, because usually Qwen vision is doing its job good. In order to get to transform LLM into an embedding model, we added LoRa layers and trained the LLM only. Only LLM LoRa layers. The next thing is the Qwen Stella. Here we thought that, okay, there are a lot of text embedding models in the open source. So why are we taking like VLM, which is a language, which the L part is a language model, not the embedding model. So what if we take the vision from this Qwen VLM and take another embedding model which has already some embedding, has passed some embedding training, and just connect this with each other and try to train it. It turns out it works. So we took the vision part from Qwen 2 VL. We took the Stella embedding, which is 1.5 billion. So altogether it is a 2 billion model, 1 billion less than the last one. And we chose Stella because it was a good model in the embedding leaderboards. So in the legacy tab, it is the 7th place, which in each size, actually I have a mistake there, it's in each size it's the number 1 or number 2 model. So in MATAB there are like models which are 7 billion or even higher number of parameters, and Stella is only 1.5 billion and already 7th place there. We use the same data and more or less the same training epochs and strategy and everything else. Okay, so let's see what happened to our results. I'm going to show it directly from the Vidore leaderboard. So this is like an open Hugging Face space, and these are all the, can I move it? No, models. Like there are a lot of different submissions and companies like, okay, Alibaba, T-Systems, which is T-Mobile actually. So our model is sharing the first place with T-Systems. They have like a couple of, I guess, decimal points higher. The third place is also, this is the 7 billion, this is the 3rd billion, and we have the version, initial version of ColQuent 2.3 in the 6th place, and also the 9th place is the ColQuent Stella. So really funny thing happened here. So before like 2 weeks ago, our models are like in the first place. So we, with the team, we went to Barcelona for the MWC Barcelona event, and turns out that the T-Systems guys, the T-Mobile guys, are also there. So we kind of went to their booth, like showed, oh, you have embedding model. They say, yeah, we have, and then we look who's the first place, and at that time our models are the first place. So yeah, after like a week, we saw that they took this model and they just trained it for like plus 10 epochs and got this 0.1 gain there and moved to the first place. So yeah, we kind of did bad thing to us. Okay, back to here. So we have the results, we talked about the models, and let's see what is happening in the current research, what we are need to do in order to achieve our goals that we set. So first of all, another thing is that this embedding model is are being used for documents specifically. So for other images, like images of cats or dogs, our model is not good enough. So retrieving normal images, it is not working. So one goal is to have a universal image document embedding model. So it will work both with documents and both for images from real world. One model which is doing all. Second part is we try to have like different size of models, but for like, we can agree that for an embedding model, we don't need like these big 2-3 billion models there. So the idea is to have a small model with the same performance. Okay, and the third thing is you may notice that these numbers are quite high. So usually whenever you are having a benchmark, you are aiming that benchmark average score is not larger than 70%. So here you can see like already these top 9 models are competing with these decimal points. So we can say that this benchmark is already partly saturated. And these decimal points can even be affected from random seeding of the weights. That's why we aim also to develop a better benchmark, so people can go and see the clear differences between the models and not these decimal points there. Okay, let's see what kind of experiments we also did for so far right now. Okay, one interesting thing is that LLMs are trained to generate like textual information. So if you're using LLM for an embedding, maybe not all layers are needed there. Maybe the last layers closer to the LM head layers are specifically there for generating text. But for the embedding, we don't have any generation. So having this hypothesis, we went and like clipped the last couple of attention layers from the LLM, the first one. So instead of having 36 attention layers, we have like clipped different number, 9, 18, and others. And we saw that even with the 9 layers of attentions instead of 36, the score doesn't go down as much. So for this one, the original score with the 36 layers was 90. And with 9 layers, we had a score of 87. So like the difference is not big, but we are cutting a model by much. So the 3 billion model has been cut to 1.7 billion model there. The other idea is to do the CLIP-style model retrieval training. So for usual VLMs, from vision part, tokens are going to LLM, like this process. So why do we need to give vision tokens to LLM? Why it needs to be proceeds to it? Because we have the vision encoder, maybe it's enough. So similar to CLIP, we say the image is going only through the vision model, and the queries are going through the LLM, and the rest of the training is happening. So we kind of cut the part for all the images. We cut the LLM out and only keep the vision model. With this training, we also trained the LLM, and the results were around, if I'm not mistaken, 85 compared to the 90. So that's also there. And also we try to train even smaller VLMs. So for example, we connected the Qwen 2.5 with Qwen 2.5 LLM. So there is a vision model Qwen 2.5 3B, but there is no vision model with this small LLM. So this is just the vision encoder and LLM connection. And it's also giving like good results. I think it was around 85 score. And there are like other small LLMs even lower than 500 million parameters, like small VLM stuff. Those experiments, I don't have numbers because they are like currently training. I can give updates like in a week. And as said, as I already said, the better visual document benchmark, because current Vidore has some issues. As I said, the scores are saturated for models, so we saw that some query matches to multiple images, but only one is the ground truth. So if our model like predicts the second one, which is also correct as a prediction, because the ground truth was the other one, our score is 0. There are like these kind of incorrect cases in the benchmark. And the other issue, one of the other issues that is not multilingual, mainly the datasets are in English. And the other thing is that some of the queries are too general. So in some of the datasets, we saw that, for example, there's a query which says, what is the page number? I mean, all the document pages can be retrieved for this question, because almost all pages, besides except the first and the last one, has page numbers there. And there's only like one ground truth for this question. So if our model is lucky to choose that image, then good. If no, then 0. So having done this research and seeing these results is the thing that kind of motivates us to go for a better, for creating a better benchmark for this task. Okay, I think that's it. So This is my LinkedIn, and also I'm putting the Hugging Face page of Metric. You can go there. We have like all these models there. You can also see what are the other research direction that we are doing. Let me quickly also show it. That's this. So this is the document rack models. We have interesting research direction in Armenian LLMs and embeddings here. And also we have recently published the Armenian benchmark here. Okay, so make sure to go download, like these models.
Are there papers?
Currently no, but we are in process of formulating and writing it. Okay, let me go back here, make it full screen, and thank you. If you have any questions.
I understood you correctly. Your retrieval approach, you just try to find the area inside the source image document without recognize the characters. Just try to split the documents and try to find the relevant area to the input text query. Am I right?
Yes, you can say.
Okay. So I just curious. Traditional approach when we have OCR, it's still relevant because sometimes we need not only documents, but also we can find the relevant areas and after that apply OCR, for example, to try to generate answers with LLM. Okay, thank you.
Thank you very much. I have one question. Are there any approaches to make a multimodal embedding? I mean the document with its text retrieved with the OCR. Are there any approaches to embed the document not only with the vision transformer, but also with its text to have maybe better embeddings or better understanding of the content?
Not that I'm aware of, because usually like for these VLMs, they are good enough to understand text themselves. So like the Quen, you can give the image to it and say, give us OCR, it will do the OCR. So additional image is not, additional text might not be very helpful. But I believe we can like easily extract text, attach to like document tokens, and give it as a input. In terms of VLMs, I know the layout LM that they are working on top of OCR, but they are like not specifically embedding models. But you can like do the same training with the layout LM. However, the key point is that we need to get rid of the OCR part and OCR engines, because they are like not convenient and like takes too much time. Basically, that. Question over.
Yeah, thank you. In your attempts to reduce the size of the model, you said that you were reducing the number of layers in the attention head, and you went from 36 to 9. And I want to ask how the 9 came about, because it doesn't seem like a very obvious choice. Is it like the best working number of layers, or was it intuition?
Actually, I think the idea was to cut it on half. So 36, then 18, then 9. And we also tried lower than 9, but in that case it was not working good enough. So the lowest acceptable number, And I mean, we don't have enough resources to try each number, of course. So we kind of went with the cutting with 2 strategy, and the lowest one that give us good results was 9. So with 18, we got higher score than 9, but it was very similar. So why 18 if you have 9?
Are you really think that you can build a model, a universal model for vision to text? I think this is impossible because it's AGI problem.
It's what?
It's AGI problem.
Okay, it is not possible because there is already such kind of model. So, like in the leaderboard, we have this Alibaba embedding, which is a general embedding model. However, it is, as you can see, it is not in the first place in the document field. So, but it is the 8th one and quite close score. So if they did it, I mean, we can also do it, and we are like trying to do, this is like 7 billion parameters. We hope to get similar results or even better with lower parameter model.
I say that the problem to convert a picture to text, it's high abstraction. It's a artificial general intelligence problem to do that. If you say that you try to build universal model, see, if model, no problem. If universal, this is mean that.
I mean, yeah, I get it. So universal in the retrieval part only, not in overall. I mean, in a retrieval only. Yeah. For document and image, I called that universal, but we can work on the naming as well.
Okay.
Okay. Any other questions?
First of all, thank you for the talk. It was very clear and concise. And the question was not about the model actual, but about the search, about method searches. You mentioned BM 2.5, and this is from classic era of information retrieval, and neurals, or as I can understand, it is approximate neural neighborhood search. And what is hybrid search? I don't understand what it is.
The hybrid is a combination of BM25 and vector search. Like you do both together, and you get the top like n results from having BM25 and hybrid, like the vector search together. So it's a combination of them, like ensembling of both.
So first one applies approximate neural number search. Okay, thank you.
I guess we're done.
Thank you.